Okay, how's everyone feeling today?
Totally.
All right.
Wait, did we finish lesson 1?
We're going to finish it right now. Yesterday we were talking about how to identify different capacitors. You know, we had to identify different capacitors because some capacitors can hold more charge than others. Yes?
Hey.
Hey! So, we were comparing these two capacitors here, and let's say they were uncharged to begin with, neutral, and let's say the capacitor on the left was connected to a 12-volt battery, and when the capacitor on the left was connected to the 12-volt battery, the negative terminal electrons are repelled and make this plate here just as negative as this piece of metal right there. That terminal is negative. And the positive terminal here is connected to this other plate right here, and the electrons get sucked off of this plate right here, and basically because they're attracted down to the positive charge, leaving a positive charge behind. And let's say that the charge on this capacitor is basically, this one here has a charge of negative 36 coulombs, and this plate here has a charge of positive 36 coulombs. If we were asked, hey, how much charge does that capacitor have? Well, the charge on that capacitor would just be stated as 36 coulombs. Now, let's say that the wires were disconnected from that capacitor and connected to
Mr. S.
Yo.
Do the positive and negative sides of the capacitor, do they have to be equal?
Yes. And let's say that same 12-volt battery was connected to this capacitor, and basically this plate became negatively charged and this plate became positively charged. But maybe this capacitor over here, even though it was charged by a 12-volt battery, maybe it only stores up 24 coulombs of charge. And the question is why? Why? Why would this capacitor over here end up having less charge when it was charged by the same exact voltage battery?
I'm a little confused.
Yeah.
Both ends would just go to the positive?
No, that's a big mistake that I made. Thanks for pointing that out. Okay. Whoa.
Hey, you did a good job. Got it. That was like first and third person at the same time.
Come at me, bro.
Much better. Thank you, Diana. All right, so basically, folks, the capacitor on the left is able to store more charge when using the same voltage battery. So we want to identify that capacitor, as being like a bigger bucket of charge, yes? And to identify the capacitor, a new term is defined. It's called capacitance. And the capacitance is defined as how much charge gets put on the plates, this is a Q, compared to how much voltage is hooked up to the capacitor. So, for example, the capacitor on the left, the capacitance would be 36 coulombs when hooked up to 12 volts, or you could say that would be what? 3 coulombs per volt, whereas the capacitor on the right would be C equals, let's make this let's make this 24. 24 coulombs over 12 volts. So the capacitance of the capacitor on the right would be, whatchamacallit, 2 coulombs per volt. Now, to honor a scientist whose last name was Farad, a coulomb per volt is also called a farad. So 3 farads. Or 3F. And basically what this tells us, if this capacitor over here was hooked up to a 1 volt battery, not a 12, but let's say it was hooked up to a 1 volt battery, well, this tells us that there would be 3 coulombs of charge put on each plate for the 1 volt battery. And if this capacitor right here was hooked up to a 2 volt battery, well then how much charge would be put on each plate? 3 coulombs are put on each plate for each volt, yes? So if it was hooked up to a 2 volt battery, how much charge would be on each plate? Samantha?
18.
No. 3 coulombs for every 1 volt. And if this battery right here was 2 volts, it would be 6 coulombs.
Oh, I thought you meant like to change the top. I mean the bottom number from the 12 volt battery.
See, the thing is, once you have the physical structure of the capacitor, okay, once you know that it's a 3 farad capacitor, its capacitance doesn't change unless you like change the size of the plates and the distance in between them. So basically, once you establish it's a 3 farad capacitor, that doesn't change. What ends up changing is the Q and the V. This here stays constant as long as the physical structure of the capacitor isn't changed. So once I establish that it's a 3 coulomb per volt, it's going to stay 3 coulombs per volt. And now if I hook up a 2 volt battery here, yes? Well then, how much charge would be put up here now? It would be 36?
Yeah.
No.
I thought that doesn't change.
No, the capacitance doesn't change. The capacitance doesn't change. The ratio doesn't change.
Like it's always gonna be, like for that it's gonna be 3F, so you have to adjust the other things so that it always equals 30.
So then it would be 6.
It'd be 6 coulombs. You know,
With all of this is
The charge.
the charge on this capacitor right here.
You're solving for Q, and
So-
3 becomes 2.
Let's say I take that same identical capacitor right here, yes? And let's say it's neutral to begin with. And on the side of this capacitor, it says C equals 3 coulombs per volt, or it says 3 farads. Once a capacitor is built, its capacitance stays the same. Okay. Now, if I take this capacitor, and let's say it's neutral to begin with, and I hook it up to a battery that's 2 volts, yes? See, this is negative, this is positive, this becomes negative, this becomes positive. How much charge would be put on the plates now? Well, we know that capacitance is equal to the amount of charge per volt. This particular capacitor has a capacitance of 3 farads, but I hooked it up to a 2 volt battery this time. So this time, how much charge would be put on the plates? It's going to be 3 farads times 2 volts, yes? But that's equal to 3 farads. You always got to remind yourself that that's a coulomb per volt times 2 volts. So basically the volts end up canceling and you get 6 coulombs of charge. Yes? So what is it about this capacitor that it's able to hold more charge as compared to this capacitor? Well, it turns out it depends on two factors. The area of the metal plates, and two, the distance between the plates. Yeah.
Do you mean like surface area?
Yeah.
Oh, okay.
So I'm going to draw a three-dimensional picture now. Because remember, like if I held these two sheets of paper right next to each other, that's like the capacitor right there. You know, we've been looking at the side view. Two sheets of metal like that, piece of sheet metal, piece of sheet metal. So I'm going to attempt to draw like a three-dimensional picture here like this. So, I go up at a 45-degree angle. It makes it look as if it has depth. Good enough. One more time. Keep curving. Okay, so basically you have these two parallel plates, yes? The area of the plate, like right here, which is going to be equal to the area of the bottom plate. They both have the same area if they're parallel, if it's a parallel plate capacitor. The area of that plate right there is A. And then the distance between the plates lowercase d and if you know those two measurements, you could calculate the capacitance of the capacitor. The capacitance is going to equal epsilon 0, which is a constant, I'll give you that to you in a second, times the cross-sectional area divided by the distance between the two plates.
So it's not surface area. It's cross-sectional area.
Well,
I think 3D. I think each plate has that, doesn't it? Like,
There was a sheet.
it's a sheet, so like if this was a piece of metal and this was a piece of metal,
well, it still has width.
okay, it does still have width. So it's not the complete surface area, no. It's the area of the largest face. Like this right here.
Okay.
So these were the two plates.
Got it.
It would be this area right here.
And only one of them, right? Not both.
Right. So if you have a capacitor that has bigger plates, bigger area, is it going to have a bigger or smaller capacitance? Diana? Bigger capacitance. And does that mean it can hold more or less charge? More charge, yes? So it's like a bigger bucket of charge that you could splash on somebody, yes? Now, could you have a capacitor that has a lower capacitance, a capacitor with a lower capacitance? Could you have a capacitor that has a lower capacitance have more charge on its plates than a capacitor that has a higher capacitance.
Yeah.
Depends the voltage.
Yeah, it depends on how much voltage you use to charge it up. You know, so you have to be careful about that. Did you follow me on that or no?
It's the ratio.
It's the ratio. Like this. If you have this capacitor here, and let's say this one here has big plates, you know, and oh my goodness, they're so close to each other. Yes? Okay? So the capacitance, let's say, is, you know, 120 farads, yes? And then you add this one over here, you know, small plates, and they're like way far away from each other. They're supposed to be the same size. And then let's say the capacitance of this one here is 2 farads. And to begin with, they're both uncharged. They're both neutral. Yes? Now, is it possible to put more charge on the capacitor with the lower capacitance? Yeah. You know, I could connect a 12-volt battery to this guy here, yes? And if I did that, how much charge would it end up having on it? Oh yeah, that's just like before. And meanwhile, over here, I could use a battery maybe that you use in a watch or something, you know, has a very, very low voltage of, let's say, 0.1 volts. And I connect it to there. Yes? How much charge would that sucker have on it now? So even though this capacitor over here has a bigger capacitance, does that necessarily mean it's going to have more charge stored up in it? No.
But when, like, is that like realistic to have like such a small charge, such a big capacitor?
I mean, I'm just saying it's possible. In other words, it's kind of like compared to this question, Justin. If I have 2 buckets, a big bucket and a little bucket, can I have more water in the little bucket than in the big bucket?
Sure.
Of course. Of course. That's the point I'm trying to make. Okay.
Great analogy.
Thank you. They just gave me a compliment. We're being recorded.
Oh.
Okay. So, moving on, ladies and gentlemen.
Any jokes today?
No jokes today.
Thank God.
Any demonstrations?
Okay. Demonstration coming.
Oh yeah.
Okay.
I do it.
So,
No.
I want to show you another use of capacitors. Capacitors can also be used to deflect beams of charges.
Charge. Just a weight.
Kidding.
That's just a weight.
Like,
A lot of questions today.
Good luck, Science Olympics team from Syosset.
It's like some
I think
crazy.
they do really good.
I think they did
Yeah.
really well. I thought they did really well.
Yeah, well.
They do.
You're in trouble now.
Guess it's not gonna be used. Just start screaming.
Okay, so how can capacitors be used to deflect a beam of charged particles? I want to show you this process called thermionic emission, which is used to generate a beam of electrons, and then I'll show you how we could use capacitors to make the beam of electrons go up and down, left and right. And then I'm actually going to bring out one of these devices so that we can see it firsthand. Okay, thingamabobbers. So this is going to be a big diagram here, and we start off with a metal filament that goes down to a point. So it's like a piece of metal. Usually made of tungsten. And down here we're going to have a battery. And this battery over here is negatively charged on that terminal, positive on this terminal. And we're going to connect the negative terminal of the battery to the filament. Go around on the side because we're going to need some space in here. So over here is the battery. And once you connect that negative terminal to the metal filament, electrons repelling each other on that negative terminal are going to move up that wire into the neutral territory of the metal filament. And moments later, this metal filament is going to have the same concentration of electrons as the negative terminal. Yeah.
Wait, you know for the E0 thing, you never get.
Oh. Diana, that's the second,
100 on the quiz.
you're rock and rolling today. Okay, epsilon 0 is always given. It's called the permittivity of free space. Okay,
Excuse me?
it's 8.85
Wait, one second. I'm sorry, free space. Okay. 8.85.
times 10 to the negative 12 Coulomb squared over Newton times meter squared.
Oh, easy.
So it's like the opposite of the other.
Yeah.
Okay.
Okay. I'll maybe thinking something.
How's everyone still feeling?
Yeah.
Still,
Excited for the demonstration.
All right. You know, back to the capacitance. Yes? Most capacitor problems that you'll be exposed to on the AP exam have air in between the two plates. So you only need to use epsilon 0. Okay? However, if the capacitor did have another material in here, like a piece of glass, piece of plastic, yes? Well, then there would be another K term over here, and it wouldn't just be epsilon 0, it would be kappa, I'm going to call it K prime, epsilon 0. This is not K like 9 times 10 to the 9th K. This is a different K. Every different material would have its own K value. I believe on one of your homework problems, you have to do a capacitor problem, and they tell you that there's a certain glass in between the plates. So look back in the chapter, find the constant for that particular material, and adjust your formula. Okay, obviously, what's the K value for air? 1, and it just drops out. This K right here is called the dielectric constant, because the material inside the two plates is called a dielectric. Alrighty, so getting back to this question here, how can capacitors be used to deflect a beam of charged particles? Okay, we're going to look at this process called thermionic emission. We take a piece of metal connected to a negative terminal of a battery, it becomes negatively charged, and now what we're going to do is heat that piece of metal up. We're going to take a second heating coil and place it underneath that filament and connect that to another battery. When electrons go from this terminal through the coil, they heat up the coil, similar to the coil in an electric toaster. The coil gets like red hot, starts giving off heat. That heats up the metal filament. The metal filament, made up of metal atoms, those atoms start to vibrate with more kinetic energy because the temperature is rising. And eventually what happens with this metal filament is not only do the atoms start vibrating faster and faster because of the heat from this heating coil right here. So that's it. But the electrons themselves start to move around with more kinetic energy. And they move around with more and more and more and more kinetic energy until finally some of the electrons actually jump off of the metal filament. And when the electrons gain so much kinetic energy that they jump off the piece of metal, that's called thermionic emission. Now over here is another metal structure that looks like a donut, like this piece of tape I'm holding, a roll of tape. Okay, and basically this piece of metal is connected to the positive charge of the battery. So I'm going to attempt to draw this like three-dimensionally here. Try it again. I'm not doing the best job of doing the three-dimensional thing there. But if we connect a wire to this, electrons are going to be sucked off of that metal ring. And if electrons are sucked off as they go towards the positive terminal right there, you know, what kind of charge is going to be left behind there?
Positive.
Are you positive?
No,
No.
neutral.
Good.
We use that one.
What is that exactly?
It's a donut-shaped piece of metal.
Okay.
We're trying to draw a three-dimensional picture of it.
Alright, okay, I get it.
Why is it donut shaped?
Well, here's the thing. These electrons that got ejected over here due to the intense heat from the heating coil, they're going to be repelled from the metal filament over here, and they're going to be attracted towards this positive donut ring over here, yes? So these electrons are going to start to go.
Does it have to be that shape? Or is it like any shape?
It's usually circular, and here's the reason why. Let's say I'm this electron right here, yes? Okay? And let's say that that door is in the shape of a ring, and let's say the door is positively charged, yes? Now, some of the electrons, yes, that aren't quite perfectly centered, they might be attracted and go right to one of the sides, yes? But some of the electrons that are ejected right down the middle, yes? Okay? If they're going right down the middle, and they're attracted to that side of the door, which is positive, and they're also attracted to that side of the door, and it's like an equal pull, yes? And they're attracted to the top and the bottom equally, yes? Guess how that electron's going to end up like moving? Straight down the middle of the ring, yes? Faster and faster, and they go faster and faster and faster, whoa, right through the middle of the ring, yes?
Shoot electron.
So basically what you end up getting is a beam of electrons going
Why don't they stick?
right through.
Because there's an equal pull everywhere.
So the oh, okay.
So they pile through the center.
So they come through the center. And you get this beam of electrons.
Be used for what?
Like light.
Hold on. Now before we see what this beam of electrons is used for, a very popular question is how much or how fast is the electron going when it goes through that ring right there, yes? And let's say we know the voltage down here. Let's say it's a voltage V. If we know the voltage of the battery that was used to charge the metal filament and the ring over here, whatever the voltage is between these two terminals of the battery, that's the voltage difference between these two structures up here. So if we want to know how fast the electrons are going, it's going to require two formulas. One, V equals W over Q. If we rearrange this, we know W equals V times Q. V is a given because it's the voltage of the battery. And we also know Q because what are we dealing with here? Electrons. And if we're dealing with electrons, we know Q is going to equal 1.6 times 10 to the negative 19th coulombs. You know, it's actually a negative Q because it's an electron. Therefore, we could solve for how much work was done as that electron went from here down to the center of the ring. And if we know how much work is done, recall from an earlier lesson how the work done on the electron equals the electrical potential energy at one point equals the kinetic energy at another point, yes? So basically, if we know how much work is done on that electron as it goes faster and faster towards that positive ring, we also know how much kinetic energy it gains. So basically, the work done is going to equal the gain in the kinetic energy. And then once you know what the kinetic energy is, how can you find the velocity? You go, Diana. You are rock and rolling today.
Wait, so can you simplify that as VQ equals 1/2 mv squared?
Yes, but be careful because this is big V voltage,
Oh.
and this here is little v velocity. Thus, the speed of the electron can be determined through that ring.
So you could do 1/2 mv squared, wait, did you set that? Like,
Yeah.
okay.
Wait, can you go back one slide? Or, wait, no, actually go forward. I thought it was on that slide. Wait, back.
This?
Yeah, the electrons. Oh, never mind. Okay, good. I got it. Thank you.
Oh, actually, I have a question.
Yeah.
So, like, I know the charge of electron protons like the same, but when you have an electron right negative, like in like all the different formulas, like like corresponds like K equals 2. So when it's electron, it's negative.
If it's proton, it would be positive that. Okay. So now we have the beam of electrons coming through the ring. Now, of course, as that beam comes up forward this way, yes, okay, what's this positive ring going to do to it? You got a negative charge coming through.
Neutral.
Okay,
Go back.
Attract, but it's on every side, so it's not really gonna move.
it's going to like
Go back.
pull it back.
But it's gonna accelerate it at first.
Yeah, it's going to accelerate, make it go faster, you know. And, actually, if it went over here, that same thing would be pulling it back. But it's going to be going so fast now that that positive attraction back isn't going to be enough to slow it down. Remember over here, not only was it being attracted to the positive, but it was also being repelled from that negative. So we had like a double kickarooski here, making it go faster. And of course, when it gets over here, this positive ring might be like slowing it down slightly, but usually that's like neglected, not even talked about. So now we have a beam of electrons moving along. We know how fast the electrons are going. Now we're ready to talk about how capacitors can be used to deflect the beam of charged particles. Y'all ready for this?
Wait, isn't the mass of like an electron like negligible? Do you know what I mean? Because I remember in chem, like when we talked about like atomic mass, like it was almost neglected, like what an electron is. So like when you have 1/2 mv squared, like what's m?
It's actually like 9.11 times 10 to the negative 31st kilograms. It's like 2,000 times less mass than the mass of a proton.
Right.
2,000 times less mass than the mass of a proton. But nonetheless, it is some mass.
Yeah, because like if it was 0, it would be no point.
Right. So, it does have mass, so you could still use that mass to get the kinetic energy. It's just much less than the mass of a proton and a neutron. That's why you remember from chemistry, you just basically neglected it.
Okay.
Okay. So basically, let's take and put a capacitor here like this.
Should we like redraw it?
Well, hopefully you still have room on the right, as I do.
Luckily, I don't. Wait, now capacitor? Oh god.
Because I got to fill in this whole screen over here yet. So this here is a And this over here is a variable voltage source. One wire connected to here, one wire connected back there.
So like, what's the difference between that and a battery?
This one here has a dial,
Oh, you can adjust the voltage.
and I could dial it this way, and it'll make this top plate positive and the bottom plate negative. Or I could dial it back to the center and the two plates become neutral. Or I could dial it to the left and the bottom plate becomes positive and the top one becomes negative. Now if I dial it this way so that the top plate is positive and the bottom plate is negative, then guess what that electron beam ends up doing? Does it end up going straight through like that?
Oh.
No. It ends up getting deflected upward, yes? Because it's going to receive an upward electrical force, so it ends up curving upward ever so slightly like this. Ready? Watch. It's going to be like a slight parabolic upward curve to it, yes? And then as soon as it comes out over here, it would just continue, going straight.
Right now, when these things are like set up, like let's say like you do this in an experiment, like that metal ring and like the metal film and stuff, like the things that like those obviously don't like float on their own. So like when they're mounted to things, like are they like coated in like non-conductors?
Yeah.
Insulators?
They're probably like held by a
like rubbers and stuff.
like piece of plastic so that they stay charged.
Right.
Yeah, because they're not floating in the air. It's absolutely right. If we take a closer look at this, folks, you're going to love this. Ready?
Oh.
Whoa. Whoa.
Wow.
We can see the electrons. Whoa.
Oopsie.
Nope.
Someone, really sloppy.
Right here, in between the plates, if the electron continued going straight, it would go like this, yes? But it ended up curving upward, so it rose this vertical distance here upward.
So you have to calculate that.
How the heck do we do that? I don't know. Look, look where I have look what I'm drawing.
Okay. And if we happen to know the length of this plate right here,
Alright, we can like print this out.
okay, basically, we could calculate that lowercase d there, how much the electron was deflected. Now here's the deal, folks. See if you can follow me on this, yes? As the electron came into the plate here, yes? Here it comes, right through, yes? Does the electrical force, which is acting this way, have any effect on the speed of the electron, which is this way?
No.
So what do we know about the motion in this direction? Huh? Constant velocity, uniform motion, yes?
In which direction?
In this direction. That's where we're going, ladies and gentlemen. They're back.
No.
Projectile motion problems.
Are you kidding me?
With the horizontal and the vertical,
Yeah.
Yeah.
Our
No.
favorite.
the electron is going this way with a constant velocity. Meanwhile, what is it doing this way? It's accelerating that way. So once again,
Funny.
we're going to have to set up
You gotta be kidding me.
a horizontal column for the horizontal motion and a vertical column for the vertical motion, yes? And what's the acceleration in the horizontal direction? 0. And usually when we studied projectiles, what was the acceleration in the vertical direction?
But it's positive because it's going up.
Yeah, but this time it's not going to be like 9.81. It's not going to be 10. Because it's not the force of gravity.
It's the force in the field.
It's the electric force, yes?
F equals KQ on the R squared.
So here's the deal. To get this guy right here, okay,
It's definitely gonna be our part.
see next page.
I have a question. Doesn't the acceleration accelerate as the distance keeps on changing?
What's that?
Just like your
Like-
voice.
Sorry, I'm eating.
Oh, okay.
Doesn't the distance get smaller so like the force changes? Like
No, because with
Thanks.
a capacitor, if we take a look at the invisible electric field that's exerting the force, and this gets even a little bit trickier yet, because which way is the force on the electron?
Up.
Up. But if we wanted to visualize the invisible electric field, the name of the game
What's in front?
is use a little positive charge, and if you put a tiny imaginary freedom move positive charge, which way would it move?
Down.
Down. So the electric field lines would be going down, 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 down. Are those field lines diverging?
No.
Are they converging?
No.
So what does that tell us about the strength of the field?
Equal.
Uniform throughout. So therefore, Cindy,
Why do you do this to us?
the force stays constant the whole way. Just like the force of gravity stays constant. Yes? So the question is, how, when the electron is going through, the electron experiences an upward force, because the field lines show what a positive charge would do. And what we're trying to do is figure out what is the upward acceleration of the electron. Well, we know that from law number 2, from a man named
Ton.
the net force pushing that sucker up is equal to the mass of the electron times the vertical acceleration, yes?
Is everything we've learned up to now.
Yeah,
But-
we don't know.
No wave. No, really, no waves.
The electric field strength
That's good, Justin.
is equal to the force
Come together.
per charge. So if we know the electric field strength, we could get the force by multiplying the electric field strength times the charge. But the question is, how do you get the electric field strength? Well, the electric field strength you could get from that formula, remember? V equals E times D. This is for the parallel plate capacitors.
Never learned.
Let's take a look at that then.
Wow.
Okay? Let's say you wanted to do work, and you wanted to do work to move a charge from one plate to another.
We learned
You know how work equals force times distance?
Yeah.
Yes? Well, with electricity, it's more convenient to talk about the work per charge instead of the whole work. And it's more convenient to talk about the force per charge instead of the whole force. So if we rearrange this and solve this one for W, we get VQ. If we rearrange and solve this one for F, we get EQ. Not GQ, that's a men's magazine, that's different. This is EQ. Okay? Now, if we put these two over here, what is W? Well, that's VQ.
Yeah.
What is F?
F
That's EQ times D, and voila. Hasta la vista, Q. And what are we left with?
Should we like write
V
that with
equals
our parallel
B,
plates? No?
D.
Stress?
But D equals D over
D is
D.
voltage, right?
No,
So
no,
what
no,
is this
no, no.
representing?
E equals what?
But you have to be careful because this D is not how much the electron gets deflected upward. What's this D?
The distance.
Distance
The distance between
between
capacitors.
the bars.
Wait, E.
It's that D.
Wait, so wait, the D. Wait, the E is
So basically, folks,
what?
use this formula to get the E. Once you have the E, you could put it into this formula to get the F. Once you have the F, you can put it into this formula. Oh, no, no, right, skip that. Wrong turn. Wrong turn. Once we get the F, we can put it over here into this formula.
I don't get it.
Now, what about this mass right here?
Mass of the electron.
Mass of electron. Hannah, you go, girl.
And wait,
You are doing
with
a great
the
job.
A.
And now,
You are on track.
we have the upward acceleration. So we could go back now and start the projectile motion problem.
Started. Okay.
You know?
Oh,
my
that's
God.
the start.
This is incredible.
I got it.
Who cares?
Don't we just like
I need a therapist.
You know what I mean, people?
No.
Can I go to Miss
Why
Taylor?
are you so-
And you're going to have to use formulas like D equals VIT plus 1/2 AC squared.
What's that?
Beautiful.
It's X.
Great
What are you
X, D, L, S. It's all the same.
No, it's not.
D equals VIT plus 1/2 AT squared.
I'm gonna do it.
That's a little flash from the past.
Oh my God.
I'll leave that for you to try on your own.
Here, calculate this.
Do we know the V?
Yes, yes.
Can we all be quiet? So what is AY? I'm so confused.
You put the F into F net equals MA, and then you
Remember
solve for
with projectile motion problems, we needed a horizontal acceleration
Wait,
and a vertical acceleration.
Did you just say wait?
AY is the vertical acceleration.
Right.
How did we get AY? This is AY right here.
Can you just pause on this page for a second?
Order.
No, I need to copy this page.
Order.
What did she say?
Wait, hold on. Just leave that up for a second. Alright, let's get rid of this.
So what's the point of E equals VQ? I mean, wait, that's not a
We are going.
Well, I just rearranged, that's the most common form of the formula, and I just rearranged it into F equals EQ.
Don't you have a Bill 9 video?
I used to work with a physics teacher,
This. Okay.
and this was his favorite formula.
This is Zed.
Who the heck?
Ed
Whoa!
Duncanson.
Oh, I thought it
He
was
used to do the Duncanson shuffle every time that thing came on.
Whoa!
Are you serious?
Yeah.
Yeah.
Do it again.
Do it
True
again.
story about this teacher. Again, we were both teachers up in Pine Bush, New York. Back in the 80s, there was a nationwide competition
Oh.
for high school science teachers, and basically the winning teachers were going to train at NASA, and one of the science teachers
Whoa.
was going to get to fly the space shuttle on a mission.
So cool.
That's pretty great. I knew you were gonna say that.
Ed Duncanson applied, was accepted.
Oh.
30 people were trained in Florida.
Oh.
And
Okay.
he went to space.
Okay.
No.
When it came down to the finalist,
He lost.
he came in second place.
Oh.
True story.
That is so
Oh.
sad. Wait, what is the
Okay.
What's the contest? What did it do?
The main
Ed, do shuffle.
winner,
Shuffle.
okay, was a female science teacher. I'm not sure where she was from. Now
Is that
wait.
the one who went on that challenge?
So he was the best male science
Is that
teacher.
the challenger? Oh my god, that's so scary.
That's the space shuttle
That
Oh,
blew up.
that
that's
blew up
scary.
with the female science teacher on it.
Oh, I
Oh
still
my god.
This guy was just like wrecked. You know what I mean? Because first of all, that was, you know, that could have been him. He was friends with this woman he trained with. I mean, it changed him for the rest of his life.
He doesn't shuffle.
You know what I mean? Like, from being so disappointed to being number 2.
To being like,
Now he's back.
that's like those people that didn't go to work on 9/11.
Exactly.
Yeah.
Oh,
Exactly.
Yeah,
That's like, yeah, my kid was sick. Oh my
Yeah.
god.
You know what?
One last shuffle.
Huh?
One last shuffle.
To those of you at home, Mr. S is shuffling.
Okay. Now,
So now that we have no idea how to do this round,
Wait, he trained at NASA to like, and he like went in like zero gravity and all that.
yes.
That's so cool. I want to
That's
do
so
that.
awesome.
they use like a huge pool too.
That's so cool.
They have
Yeah.
like a big pool with like a space like station in it.
All right. Now, ladies and gentlemen, if I wanted to deflect this beam down, I could turn the variable voltage, yes? And what would I have to make this bottom plate over here? Positive.
Okay.
And the top plate negative, yes?
Yes.
Or I could control the dial right here, and I can make both of them neutral, and what would the beam do?
Straight.
So I can control how the beam goes up or down, yes? Now, what if I wanted to control whether the beam goes left or right?
Oh.
Put 2 more clips
Yeah.
How?
on the side.
Yes. That's exactly what we have to do. Here we have 2 pieces of plates like this, here and here. Now we have to put 2 more plates like this. Yes? So basically we have another set, and I'm going to try to draw
It's
3-dimensional.
an electron cannon.
But I already ran away on the side.
I cannot draw on that picture anymore. I've read it 3 times. Like, I can't. 2, 3. I can't do this.
Pretty sure it's a fictitious.
To be honest, I feel so
And
smart.
this
right
class is going to make me jump off a building.
Because we're learning this. But then again, I don't
Okay,
know.
that's definitely.
Yeah, exactly. So if you don't understand.
No, actually, I do get it actually.
And these plates are connected to another variable
Copy that
voltage
for me.
source.
I want to do this.
Mr.
Jess, you're gonna make a copy of those notes, right?
No. Mr. S said.
And finally, last but not least,
Yeah, it's
we have a screen over here.
I give up.
And when the electron beam finally hits the screen,
that last.
Draw that.
there's a little coating of phosphor on the screen. And when the electron hits the phosphor, one of the electrons of the phosphor atom gets excited and then drops back into a lower level and emits light.
Oh,
And
that's
a little pixel of light will light up right there.
That's how TVs
I want to
work.
do that.
Television.
So
Are we watching?
here is like a side view. Inside the box is what we have right there.
Too soon.
Okay?
Too soon.
The screen here is over here at the end.
What is that thing?
And basically, first thing you have to do is turn it on. And when I turn it on, are we immediately going to see a dot over here?
After like a second.
No, no.
Yeah, because what do we have to wait for?
Charge.
No?
For the capacitor.
The
Heating.
Gotta heat that up to get those suckers to start ejecting.
Oh, I see it!
Look, there's
I see
light.
Whoa.
Look, and it's moving. Oh my god. Why is it moving? Oh my god, it's moving. Oh, it's moving.
Now, if
This is really cool.
I want to adjust these voltage right here, these plates right there, okay, I can do that. No way.
It's like an etching sketch.
Yeah,
Okay,
exactly what I was
See?
thinking.
I can make it go up and down like this, yes?
Oh my god, that's so cool.
I can deflect it up more, I can deflect down, or right now, right when it's in the middle, what's the deal with these 2 plates right now? They're neutral, yes? And now I can vary these plates over here, yes? And when I vary those plates,
It's on a laser.
left or right.
Oh my god.
Wait, can I try something?
Okay.
Break it,
Wait,
don't break
so
it.
what is the point of this? What do they use this in real world?
There aren't
Okay,
any-
hang on.
There's nothing applicable to
Etching
this
sketch.
ever.
Hang on. Okay. Stay with me because I want to show you this. We're running short of time. Now, there's an auto feature here with these plates. Yes? With these vertical ones. Okay? And basically, this one is made positive and this one negative, so the beam goes over here. Then they're slowly made neutral, and then this one over here is made positive, so the beam sweeps over automatically. I don't even have to turn the dial. And then as soon as it gets over here, then immediately this plate is made positive again, and it shows up over there again and goes across. It's called a sweep function. So I could turn on the sweep.
Sweet mode.
Sweet. I know how to sweep the
That's so cool.
So it's sweeping along. Now, if I control how fast it sweeps across, there's like an optical illusion.
Oh.
Guess what eventually it's going to look like?
A
if
line.
Whoa!
Oh my god!
Is this real life?
Wait, can you make it smaller so I can like see it again?
Wait, do a vertical sweep.
There is no vertical sweep.
Oh. Do it again. Do it again.
Now,
Vertical sweep.
here's the thing.
Build this thing.
True story.
Is there any application to this?
Just recently, my father, he's well and doing great thanks to modern medicine. He had to go in and get a little straw, put it in one of his capillaries. It's called a stent. Okay? And of course, while they're doing that, they're monitoring his heart. Yes? So while the sweep is on, you see these two plates right here? Instead of being connected to that, they were connected to do two different parts, on his heart. These little sticker things, they stick to him. And your heart has a little voltage itself, yes?
It's an electric
So basically, when your heart beats, this
okay.
becomes positive and negative. So basically, as it goes across sweeping, what will it do?
Oh my god.
So
Your
that's-
heart controls this guy right here.
That's
Yes?
how an EKG works.
Oh my god, this is crazy.
Now, another thing we could do is hook up this speaker. Yes? And when I hook up this
Quick.
speaker
Quick.
to these plates right here,
Quick.
okay, if we don't get to see it today, we'll see it tomorrow.
No,
Okay.
we're not gonna be here.
No.
Quick, just do
Ah,
it.
you don't have to do it.
Do it, please.
All right.
Dad, move.
Diana, out of her way.
This is going to be connected
Whoa,
up
whoa, whoa.
to the plates.
Wait, look at my heart.
Yeah, you wanna get up on my shoulders?
Yeah, sure.
You need a little bit more room?
I'm gonna get it on my
That's so cute.
romance.
And now when I talk,
Whoa!
I'm controlling those plates.
I'm totally
It's like a
doing
jungle.
that.
Sometimes I really wonder how I keep from going under. It's like a jungle. Sometimes I really wonder how I keep from going under.
That Eminem?
Wait, I'm dead. I'm dead.
Watch this, guys. The tuning fork. Watch this. This is from yesterday. Somebody said, what if we put two? Will we see the beats? Oh my god! Oh my god!
Really not that cool.
Take care, guys.
It's pretty
Wait,
cool.
no.
It really is.
Oh my god, it's